the title I thought to give it like this: N-polar AlGaN GaN HAMP for radio frequency applications. And but I guess it no, it won't sound as difficult when you move into the presentation. It's not that a difficult thing which I'm going to not discuss today. I had always kept Vaidyan in my mind when I was preparing the slides. Now I wanted Vaidyan to understand, so I have made it simple for the evening. And if you feel like I'm making it too simple, then please let me know that, no, that you don't need to make it too, this simple, so that I can, move on to more details in that case. So let me directly, first of all, let me now tell you what um, we do as a group here. Actually, I'm working with Professor Shrabandi Chowdhury um, at Stanford in electrical engineering department. And what we discuss or what we do here is, Ram, there are these transistors, the basic electronics building blocks we call, right? As we have transistors, diodes, and all. So we discuss about those devices, how to make a better transistor or how to make a better diode for different applications. So what we discuss here is which material you can use. Now we all know that for the past decades we were completely depending on silicon for almost all kinds of device fabrication. Now the material chosen was silicon, and almost all the foundries, all the fabrication techniques, all are made for silicon material. And so we have used it to an extent that now we want to move on to different materials which have better material properties for different applications. So we discuss about these materials and which material needs to be used, and how you grow the the kind of different techniques we use for growth has a lot of impact on the quality of the material. You want to come up with a good quality material, so we do that, the different kinds of growth of material in our group. And we also, after growing a material of certain qualities and all, then we need to fabricate or make the transistors on that, so that we can check the performance, and we can compare it with existing devices, and we make progress on that. So next we do is a fabrication. So we have a clean room facility here. We call it as a clean room facility where we fabricate the devices. I will discuss that in detail in the presentations, what kind of fabrications and all we do. Then we also, after fabricating, we need to do certain characterization techniques to benchmark it with the existing devices and all. And then we also need to do some modeling of the devices to see how it will fit into a circuit. When you fabricate and when you get a device, you can model that. You can get a model of the device, and then you can put that in some circuits and see how well that is going to perform for that given application. So we need to do the modeling and also a little bit of circuits and systems to see how that performs. So this is, we actually in a group, we do all these activities. Different people are given the job for different categories, and then we discuss each other. So people working in the circuits go and talk to device people, tell them that, yeah, you make something like this so that I can use it for these applications, like that. And the device people will also talk to materials people, say that, yeah, you grow something like this so that, no, this will be much better. So no, we when we do research, this is the kind of feedback you get, right? So the kind of consumers for material engineers are the device engineers. Now they consume what they grow, and the consumers for circuits are no. So these kinds of interaction between these people happens. And then we need to come up with the different strategies and all to satisfy the other group. So that's how we work here. And that's what we do in our group. So I thought I'll just give a glimpse on what we do. You all might be from different backgrounds. That's why I thought, no, this will be may give a kind of an introduction to what I'll be talking about. So in this talk, we are now, last slide I was now I'm talking briefly on devices. So here we will go for some RF devices, radio frequency devices. How do we fabricate and how do we characterize it? So here it's showing a spectrum. We know the electromagnetic spectrum, and it shows a band starting from zero point 0.3 gigahertz to 300 gigahertz. This big band. And you might have heard about millimeter wave, all right? So the millimeter wave is called from about 10 yeah, frequency goes from here to here, increasing order. So wavelength goes from here to here, right? So from 1 mm to 10 mm, this range is called millimeter range of frequencies. And I should mention here that the first person, one of the first initial scientists who started working on this millimeter waves was our Jagdish Chandra Bose. So he had worked on this in the past. And so here, even now we talk about those in millimeter wave technologies and all. So, and we haven't actually reached there. Now that's what we'll be discussing it today. So we have this band of frequencies available, and we have divided that into certain different groups even then. So for example, so we have this band, the frequencies below 6 gigahertz, and you will find different applications. Like, no, actually what all we use today is in this band only. Like for example, the mobile phone, the different Wi-Fi, the radar, initial radar connections, all these are in that range only, below 6 gigahertz. And if you but there are more applications like 5G, something which we all talk about today, about the 5G applications and all. And there are also satellite communication and what SpaceX does, and satellite internet. All these are belongs to this range of frequency. The kind of frequency they use for communication between those devices fall in this band, which is between 25 gigahertz to about 40 gigahertz range. So these band is allotted for these kinds of application. And then there are band like V band and W band and all, so which falls, now there are this 6 gigahertz Wi-Fi connections, sorry, 60 gigahertz Wi-Fi connections. And automobile, there is this automobile radar. So we talks about this self-drive car and all, right? So for those, the band allotted for those kinds of applications are about 78, 77, I guess. That's the 77 gigahertz, in that range is allotted for those kinds of application. And then we already started talking about 6G and then different imaging applications. So 6G and all are allotted, the band starting from about 40 and above to 300 gigahertz. These range for 6G, it's like, yeah, 30 to 300. This range is allotted for 6G, and people have started making devices in these frequencies and all now, which we will be eventually using it for 6G applications. So the kind of bands, so but basically what we have now in our hand is only this what we are using it extensively, and the commercial devices all falls in this range. These all are mostly in the kind of research mode of things, and the people are working for that. 5G has already come up. So this is the frequency band, which is allotted for different applications. And one thing actually I was also initially thinking out, right? So why, why people are, why they are dividing into such band? Why some frequencies in these regions are not used? Why there is some gaps are there? So why is it so? This is something I was also thinking initially. So that is actually, the reason for that is something which is interesting. So that basically falls, how the atmosphere attenuates different frequencies. That's what is shown here. Y-axis is an attenuation and x-axis is a frequency. So at for example, I was telling that less than 6 gigahertz is what is seen in our mobile phones or wi-fi's, and also that range has a very low attenuation. That's why initially, we all have those, we were using that, and we were not much concerned about this atmospheric attenuation for those range of frequencies. But when you come for this higher range of frequencies, there are attenuation from the atmosphere, basically because of the oxygen in the atmosphere and water in the atmosphere. And also there are, you see that there are these peaks in the attenuation. For example, these range of frequencies that are high attenuation, so we don't want. So mostly people concentrates on these valleys for fitting different, for example, 5G is fit over here, automotive radar is, we need to have lower attenuation from the atmosphere. That's why, it's divided into different bands, and we can only use certain bands, so that, the attenuation from the atmosphere will be less, and we will have a better communication. So this is how, this is what I wanted to give you an, introduction for the RF devices or millimeter wave devices. A high frequency range of these devices deals with this high frequency waves. And I thought to simplify the thing, I thought one of the RF device or the high frequencies, our cell phone only, it has, it receives the for 4G or 5G signal. So I thought I'd just show some block diagram based things, what is inside, or how is it processing those signals and all. So for example, I was in any circuit, let's say for even for an automotive radar application, everything will, you will find something like this, a flow of signal. For example, in case of a cell phone, we have an antenna. So the antenna will be receiving the signal. Let's say for some 4G signal it's receiving. So when it's receiving the signal, it will, the amplitude, it will be very very weak signal, right? So you need, for first thing it does is an amplification. It's a low noise amplifier, so it goes through that low noise amplifier, and then it passes through a mixer. What the mixer does is it takes down the frequency from the high frequency, from 4G or 5G, takes down to our normal frequency range. So it's it's just demodulates it, right? It takes down to our, it's remove the carrier signal and takes down our message, and then it goes to different filters, different baseband processors, and then finally it comes to the speaker. So that is the receiver path for a signal. And similarly, there is a transmitting path. So when you speak through the mic, it goes through different processes and all, and then filters and all, and then just before sending it out, it's goes through a mixer where it's upgrades, it's adds the carrier wave, and then the frequency increases, and then just before sending it to antenna, it does an amplification. It's called a power amplifier. It does a amplification process, and then it connects to the antenna. So a duplexer will be separating the transmitting and receiving path. So this is how a signal travels inside a cell phone and any other application where you need to transmit or receive high frequency signal. The block diagram will look something like this. And I was telling you initially that we work on transistors and diodes and all. So those transistors and diodes are mostly used for this application, making these power amplifiers or low noise amplifiers. And also the area I am working on, which is related to this high frequencies, will be mostly on these blocks, not on mixer or filter or any other networking operations. And also we are working on these devices which needs to amplify the signals, which needs to amplify the radio frequency signal. So you should be able to uh, amplify the high frequency signals. That's what we always now look for, amplification of those RF signals. So then the question there is, yeah, I was talking to you that there are first thing we talk about, yeah, then which material will be suitable for such applications. We want to have amplification, so we want to have high power output when you amplify it. So then the question is, yeah, okay, you have silicon, you have this is called indium phosphate, and then related other materials, you have gallium arsenide, and then related material you have gallium nitride and related material. And we also, people will also work on diamond for this application. So these are the different kinds of materials available for fabrication of these transistors, which we want for amplifying RF signals. So we need to see which material is better. Now if you use silicon, then what is going to be your performance? If you use gallium arsenide, then what is the performance? So these all actually, the property, all the final amplifying capability basically rely on its basic material properties like band gap. These are semiconductor materials. There are three kinds of insulators: semiconductors and metal. So these are semiconductor materials, so which will have a band gap between 1 electron volt to about 6 7 electron volt. So what is the band gap of the material? For example, silicon has a band gap of 1.1. Gallium nitride, on other hand, is 3.5. So we call these as wide band gap materials. Actually, our group is called WBG. It's called wide band gap device group. So that's why we work on these spectrum of devices, the devices which has high band gap. So we work on diamond and gallium nitride in that aspects. So what is the advantage of having high band gap? This basically, if you have high band gap, then we will have high breakdown field. What we mean by high breakdown field is that if you apply certain voltage across this material, and if you increase the applied voltage, at certain voltage the material will break down. Okay, so if you have a higher band gap, you will be able to apply higher voltage across the devices, so that so that it won't break down till some value. So if you have higher band gap, then you can apply higher voltage across the device. If you can apply higher voltage, we know the power is product of voltage into current. So if you can higher voltage across, if you can apply higher voltage, then you can extract higher power from that, since power is proportional to voltage. So which means if you go for wide band gap materials, you can get high power output from the device. So that's why, when that's kind of a motivation why we want for gallium go for materials like wide band gap materials. For high voltage applications or high voltage capability, you need high band gap. And the next one, I was talking about frequency, right? You just don't need voltage or current. You also need them at high frequency. So when you talk about high frequency, it's like when you talk about a device, a transistor, we know that there is source and drain. So you want the electron to reach from source to drain in very short time, so that it can be used for a high frequency application. So if the electron can move at a faster speed, then it can be used for the velocity of these electrons. All are basically depend on the material properties, material quality, property. And also, if you see the maximum mobility or maximum velocity, saturation velocity for silicon, it's about 1 into 10 power 7 centimeter per second. So this is the saturation, maximum velocity at which an electron can move in silicon material. But if you go for some materials like gallium nitride and all, you can move at a faster velocity. Or mobility is also a measure of it's also a measure of how fast it can move. So basically, what point I wanted to make is that if you have a higher mobility or higher saturation velocity, it's good for high frequency applications. For example, here indium phosphate has even higher mobility, or gallium arsenide has even higher mobility compared to gallium nitride. And also, if you are only looking for a high frequency application, these materials are much more suitable for such applications. And gallium nitride also got, it's not very bad compared to these numbers, so we all can also use it for high frequency. So this is how you select different material for different applications. And next thing is, we are talking about the voltage here, we talk about the mobility. Then we also know that the current is, if you have more electrons available, you will get more current. So if you can have more of the electrons in the channel, you can get more current, hence more power. We in voltage into current is the power. So if you can have higher current, that's good, right? So also when you have higher current, there will be higher temperature generated in the, we want that to be low as possible. We don't want it to heat it to very high temperatures, or we don't want our phone to get heated up, right? So don't want that to happen, for which you need to have high thermal conductivity. If you have a high thermal conductivity, the heat will dissipate properly. So that's if you go for diamond and all, diamond has got a very high thermal conductivity and all. So these decides at what current you can operate your devices. That's also good for these GaN, AlGaN, or diamond systems. That's why one reason we go for these wide band gap materials for high frequency, high power applications. Okay. And there are different figure of merits and all to compare. I'm not going into that thing. So I just wanted to give a feel, right? We are looking for high frequency amplifiers. For high frequency amplifiers, the devices needs to operate at high frequency and high voltage and high current. So these, if you have these sort of material, it's very good for that. Okay, so that's why we also work on gallium nitride. And a little bit more. That's was that this is a motivation just based on the material properties. But when you make the devices, and then when you measure actual output power at different frequencies, and for different material systems, like gallium nitride, gallium arsenide, and indium phosphate, you see that at a given frequency, let's say 10 gigahertz, you can have higher. This is from different literature reports, and also you can have higher power output with gallium nitride materials. That's why we are going for gallium nitride. But when you talk about very high frequencies above 10, above 100 gigahertz and all, the if you just look at the frequency, indium phosphide, I was showing you the mobility, it has got a very high mobility for indium phosphate. So indium phosphate performs better here. But actually gallium nitride materials is also, the research on that is also going on. So we hope that as the time progresses, the gallium nitride will also go high to higher frequencies with even higher power compared to indium phosphates and all. That's where we, so now we are almost here. Let's say, for example, at 100 gigahertz, a kind of 8 9 range of power output is 8 watt, or sort of power output is reported in the literature and all, for a gallium nitride materials. And another, so this is just showing an commercially available devices. One is a gallium arsenide based device, and one is a gallium nitride based one. So you can see that the device footprint, the area of the device is kind of much better in case of a gallium arsenide, gallium nitride based devices. So these are now commercially available ones. So with that, enough of in motivation on why people wants to go for gallium nitride for for the emerging applications, high frequency, for why GaN for 6G, why GaN for automotive applications. So these are the basic reasons why we try for the basic reasons are the basic material properties only. Then a little bit of the device physics. I know I don't, my little bit may be boring here, but the thing is, it's not just the mobility, and I just want to make a, tell you that it's not just the mobility and all which needs to consider. So these are the different, these are the measure of frequencies at which you can operate your devices. Kind of a cutoff frequency we call. So it's not just depend upon the mobility. Mobility is actually will be a factor of the GM what you see, but you will have a lot of parasitic capacitors, resistances and all, which we don't consider when we just compared the mobility or the material parameter in the other table. So you will have a lot of these kinds of parasitics which comes into play, and which all comes in the denominator. So if you have higher parasitics like capacitors, so this is something what we do after growth of the material, after getting the good quality material. When you fabricate a device, these kinds of parasitics should be as small as possible so that you can get maximum performance from that. So that's what we do as an engineer or as a researcher, how to reduce all these components and get the maximum from the material, what's the material people grow. That's what we do. And so that's what I just wanted to take you through the kind of work we do. So for example, this, I'm not going to each and bit of the channel details over here. So this is one kind of a material I was talking to you, right? So the first we need to select the material. So this is, and we grow it at different thicknesses and different doping concentrations and all these are designed such that you will have a better performance from the materials. And you can see this is a channel region where you will have the current flowing in the transistor. And so yeah, I guess you all know about the transistors. I believe that. So in a transistor we have source, drain, and this gate and a channel. So all these what we call as a transistor. So we want to fabricate something like this starting from here. That's what we do. This is a material, this is what the material science materials people give us, and then we need to fabricate the device on this. We need to make the consoles, drain contacts, and then the gate controlling the channel. These things we need to do. So what we do here is on a step by step basis. So we take this material and we know that this is a channel region, and we all know that what is the thicknesses of each layer and what is the properties of these layers and all. Then we move on to, so first what we do is we need to make source and drain contact which connecting the channel. So first we in the clean room we this is what we call as the fabrication process. In the clean room what we do, so we remove these layers when we open up the channel for source and drain contacts first. So the etching, we call it an etching of these layers, is the first thing what we do. Then we make the contact. The metal contacts will be deposited in where we removed those material, so that the source will be connected to channel and the drain also is connected to channel. That's what we do. And then we do some annealing and all to get a better contact with the material. And then we remove, so there will be an adjacent device next to it, so we don't want this device connected to the other one. So we remove the channel and all outside this device area, so that each device will be isolated. Then we what we do is we deposit the material and here in SiO2 which cover everywhere. We call it as a passivation. So this layer on, before making any other progress on the device, we deposit some material to passivate it. Then we start for the gate. So now we need, for a transistor we need to have source, drain, and a gate. A gate will control the channel. So then after passivating we start opening a region for gate electrode. So the gate needs to control the channel, so gate needs to reach here. So what we do, in step by step we remove each of these layers. And then we, before putting a gate, we put a gate oxide. Now we will have, if we directly put another material here, there will be a leakage. We don't need a gate to leak. We don't want any current to come from the gate. We want the gate just to control it. So we will put a dielectric which is not a conductor, which is a dial, we call it a dielectric, to isolate the gate from the channel regions and all. Then we put a gate, so that now we have source, drain, and the gate. Current will be flowing from source to drain, and the gate will be controlling the channel with a different voltage on the gate. There will be a different current passing through the channel. That's how the device. And then finally we remove those SiO2 and also this is how one of the device which we fabricate for this high frequency application will look like. And this is just an schematic view to show the how what we do. So we just do these things step by step. Actually, this one from a starting date to ending date, it takes about 1 month. Even it's just a slide showing what we do. So these process takes a month to complete from starting from here to here. It takes a month for us to complete. When I say, I'm just saying it simply that but you need to do different testing at each of the layer. When you do one step, let's say when you this do a etching, then you need to confirm that you have etched 5 nanometer and you have landed on this layer. Then you need to do this one, and then this needs to be very smooth. So that's I just wanted to give a feel that it takes about 1 month for us to start from there to this step. Then we take it for different characterization and all. So and there are these are something like this is a cross section, right? So from this side what is would look like, but from the top, when you see the device from the top, it will be looks like this. So now a device, this is the gate electrode, this is the source electrode, and this is the drain electrode and all. So this is how a transistor layout, we call it as a layout. Okay, so these are multiple layers and all. That's why you see different colors and all. So this is how a transistor layout will look like. This called a fishbone layout. So the thing is, if you see the gate, it looks like a fishbone, and the gate is a main feeding line is here, and then different gate fingers. So this, and you will have many of this. Like I'm just showing a finger or a 4-finger device here. So you'll have many of that, like 10, 20, like that. So this is called a fishbone layout, and this is called a comb layout. Now here, the gate, if you see the gate structure, it looks like a comb, right? So this is a gate pad and then different fingers like this. So these are different transistor layout. Each of these has its own advantages and all in terms of its frequency of operation and all. So this is now some of the optical images of the devices we fabricate here. So you can, this is one of the fishbone structure, and this is some of the comb layouts. And you can see there are now the gates is, yeah, this is some, you can see more number of fingers here. And there are some air bridge connections which connects from this electrode to this electrode. This is just going on top of these electrodes and all. This is just shorting these two. So this is kind of this is what I was telling. We do it by different layers, and it's take some time to complete from start to end. So we fabricate. So yeah, this is another device which is kind of the air bridge connections and all. So one of the air bridge is missing here. And for this device, the air bridge is not good. It's not it's just, it's sagging here. You can see that in the image. So these kinds of things we fabricate and we get at the end of the fabrication. And then you need to test it for different frequencies at 10 gigahertz. It's all showing x-axis is the input power. I was telling we need to get a higher output power, right? So y-axis is showing output power and gain. Okay, so this is a gain, and this is the input power over here. And then efficiency, it's called power added efficiency, how much, what is the efficiency of this at given frequencies. So this is not what I did. So this is one of the results I just wanted to show at different frequencies, and also I took it from the literature. At 10 gigahertz, how it is amplifying the signal when you give 0 dB. dB is the number for the power, the unit we use, the dBm. So let's say when you input 5 dBm, how you get about, yeah, about less than 20, right? So the gain is around 20, it seems. So how you get a higher output power, how you amplify the signals, and also then we need to do this sort of characterization for these devices. And then sometimes what we do is, let's say, for example, here at 94 gigahertz, the efficiency, the maximum attained is only 30%. So then you need to talk to the materials students or materials researchers to come up with a better mobility. And also then that's how the cycle happens. The materials engineers gives us these sort of materials. We fabricate the devices, as I was explaining in the previous slides, and then we do these characterization techniques. And then the feedback will be given to materials people, that if you have this sort of structure, then we may get a lower capacitance or lower resistance, so that we can improve the efficiency at high frequencies. And then that's the sort of feedback we give to devices or the material people. And then we give these devices to the people works on circuits, and then they use it in their applications, and they will have some feedback for us. So this is the kind of work we do at our lab. And yeah, that's my aim for this presentation was also the same, to give you all a feel about what we do in the lab as a group. And that's all I have. Thank you for listening, and I can take any questions if you have.